So thanks for joining for this talk. So I am Eric Perrault, part of the city of the strategy office of Renault Software Lab, which is a subsidiary of Renault. So I will try to explain you in this conference how 5G edge computing can enable on autonomous driving. So let's go on next. So first I will give you a very short introduction of about what mobile edge computing means. I briefly show you in the difference for an offboard application between a centralized or a distributed edge computing architecture. Then we will dig in detail about 5G and how it will enable the automotive edge computing. Secondly, I will describe what is being standardized, what has been standardized at ETSI level and what is still being under discussion and needs to be standardized to make a solid framework for edge computing for automotive. Then I will take a simple example to illustrate what I have explained in the first previous bullet and then make you a short conclusion. So I hope you are fine with this agenda. So what does edge computing means? I put here the Wikipedia definition and I would underline the keywords which are distributed versus centralized and edge service move service move at the edge of the network. As you can anticipate, the benefit for autonomous driving, that will mean that this is ideally suited for improved quality of service and latency, and this is really targeting real-time services. There's some data in which say that an autonomous driving vehicle in the horizon of 2020, 2022 will generate as much data over the IP cloud as 3,000 of today users. So this will be a terrible challenge for the cloud and for the IP operator if when AD will be massively deployed, and clearly the approach of central computing has to be revisited. Okay, so you have two options. Either you develop an offboard service, whatever it is, which is in a central, do you see my mouse? So in a centralized computer, so it will be hosted in the cloud of a road operator or a car OEM, or the service is hosted in a mobile edge computing. That means that it will be hosted and executed on a local server, which is very close or even co-located with the base station 4G or 5G. But to rely on offboard services, it's clear that you have to fulfill mandatory KPI. So first one is guaranteed behavior. What does that mean? That means that the performance in terms of latency and reliability must have a upper bound that you can rely on. But that also means that the behavior shall not depend on the operator, or it shall not depend on the edge host which is hosting your application. The second KPI for offloading services on the offboard is that, of course, the communication between your vehicle and the services, which is here, shall have very short latency and shall experience very reliable end-to-end communication. And last is that ideally the service availability shall be predictive. That means that if you can predict that on a short term you will lose the service for any reason because you are driving into a tunnel and you are losing the radio coverage or whatever, you want to be aware of that in advance to take appropriate action. So that could be whatever you want. So this is just an introduction. So for the 5G as key enabler for edge computing, I will split this chapter into three subparts: edge computing integration itself. So then I will talk about the slicing on guaranteed bitrate bearer, and then in advance cost prediction to monitor the service availability. Oops. So let's assume that you have a very modern car like the one shown on this slide, and you have an onboard services which is hosted by a service provider. So in normal way, in standard way, I would say the data are crossing over the radio interface across the complete LTE network, the IP network, and then they will reach the cloud server. But in some case, it would be more suited that that these data are processed on locally very close to the base station. So if, let's go to the next, sorry. If some data traffic rule are matched, a local gateway co-located with the base station can intercept and divert the traffic to this local edge server. And they can be locally processed and consumed. So the path is much shorter because they are processed and consumed very closely to where they are generated. So this is called local breakout. So these routing rules are set by the session management function of the 5G core network, and they are based on the vehicle subscription and vehicle locations. So this can be something which is pre-provisioned. So you can ask, for example, with a roaming agreement that you have with your operators, that the traffic, your V2X traffic, are intercepted by some predefined base station and diverted to some local edge server. And you can have something which I would say which is smarter, where it's more dynamic and it's not based on provision routing rule, which is based on the edge service being responsible of deciding when it has to intercept locally the data and to insert in the data path a local breakout point. However, this will be completely transparent of the vehicle. The vehicle doesn't control that. It's will be done based on the subscription that you will have with your operator. So one thing to be highlighted, I would say, is there's some difference between 4G and 5G. On 4G, if the traffic is intercepted, it will be the full traffic, so the full V2X traffic. You do not have any possibility to split between different type of message. But on 5G, you have a finer granularity. So for example, the DNM message, the decentralized event notification message, can be intercepted by the local gateway and routed to the to a local server, while other type of message, like for example, the collective perception message or the intention message, can go across, pass through the entire core network, the entire IP network, and can be processed on the cloud server. This is because the routing rule on 5G can be done on a per flow basis. Another small difference between 4G and 5G is that on 4G, if the data are intercepted, there cannot be any differentiated data treatment. The quality of service for the data which are intercepted are all the same. While on 5G, you can intercept some data and introduce some differentiated and different quality of service treatment. But again, this is based on some on what you have subscribed with your telco, with telecom operator, and you are a vehicle software developer for the vehicle. You don't care about all what you care is to connect to a service. You don't care about the data path. You do not know whether a local breakout point has been inserted, whether the local breakout point has been reselected or removed. This is not your business. So on the next slide, I will try to explain you a little bit more how this can be done for the edge service. So first of all, you have to know that the 5G core network is composed of virtualized network functions on a third party, like the service on the hosting by the edge, can only share and can get some API, some information coming from the 5G core. So let's assume that you are now driving and you are reaching a base station which is covered of this particular edge node. So sorry, there's many acronyms here. So AMF means access on mobility function. The AMF will notify the MEC services, which will notify your service that now my vehicle can be viewed by this particular edge node. My service, the service offered the service will decide that this particular edge node is the best suited to process the data. So it will decide to intercept the data, and for that purpose, it will go send a new routing rule in the 5G core across the MEC services. So for that purpose, it will write this routing rule in a 5G core entity, which is called PCF. SMF, which is registered to PCF, will get this new routing rule, insert a new local breakout point, and the data path of the my V2X data will be changed, and they will be now intercepted by this edge service. So again, this is completely managed by the service that you have offloaded on the application, which is virtualized in the edge cloud. And for the vehicle, there's no control. The only control that it has is when your vehicle makes negotiate the the subscription with your telco. So that's for the edge integration in the 5G core network, or 4G or 5G core network. So let's now talk about slicing on the dedicated beer. So this notion of slicing relies on the observation that there's a very different type of data traffic. For example, for infotainment, what you really care about is get high throughput, but the quality of service you don't really care. It can be a best effort for. But for safety critical services, what really matters for you is low latency, high reliability, but the throughput you don't care really. So 5G has defined this concept of slice. So I put here only two types of slicing. So far today, there are three types of slice which are defined. And a slice is equivalent to pure VPN or logical network which make any abstraction of the underlying core network on the radio interface. The slice may have different quality of service policy. So some may be focused designed for low latency, high reliability, and low throughput, while other will be focused on high throughput on best effort mode. They can have different billing policy, meaning that the infotainment over the slice EMBB can be paid by the car user, while the data over the slice over URLC, since they are used for the car, the driving of the car, they can be paid by the car OEM. The slice may also have some different scheduling policy to access to the radio channel and have different terminal point. Typically, a URLC slice may be connected to a local terminal point, so a server, while EMBB slice may be connected and have a terminal point, a server which is in the cloud. So you can think in the future as vehicle having two types of slice. One which is focused on data which are locally processed in the server over a URLC slice, while other are used for infotainment or whatever you want. So that means that you will typically have two or even more IP address, and you have a billing which can be different for the different type of application. So thanks to this notion of slice, you can have established different type of connectivity. I put here a subset of possible connectivity. Typically, when you do internet with your cell phone, you have a connectivity with quality indicator. So this is 5QI in 5G, QCI in 4G, which is so a 5QI of 9. This is a NGBR, so non-guaranteed bitrate bearer. That means that the performance are not guaranteed. It is targeting packet rate very low, less than 10 power minus 6, with the latency which is not really bounded, but this can be much higher than this type performances. And recently, 4G and 5G have introduced these two types of bearer, which are really focused on V2X. These are guaranteed bitrate bearers. That means that the performance is guaranteed. If you are able to establish a connection with the QCI3, the latency will be bounded to 50 milliseconds on the packet array less than 1%, 0.1%, sorry. And we establish a bearer of QCI 75, the latency will be less than 50 milliseconds and the PR less than 1%. So this bearer can be set up and established when you connect on LT, and you do attach on LT, so the network can by default create a default bearer for internet on, let's say, another bearer for you for your V2X or your automotive safety safety critical data, like this one. Or you can your vehicle can request, for example, this type of bearer. Today, the signaling to negotiate this type of bearer exists on the API, on the API exists. Alternatively, this type of connectivity can also be requested by the edge server on the edge node. The signaling to notify the vehicle about the negotiated type of bearer between the core network and the edge exists. The API partially exists, so it exists between the edge node on the 5G core network, but it doesn't exist yet. It's not specified yet at the upper level to be directly used by its application. Okay, that's it, basically. Oops. So something important is when you establish a connectivity, the performance are guaranteed between your application on the vehicle and the session endpoint. So for if you establish a connectivity between a YouTube server or YouTube client here, the session endpoint is this guy, the packet gateway as the interface between the IP network and the LTE network. So that means that the quality of service that you have negotiated is bounded between your client on this point here. But thereafter, there's no guarantee of service. So there's no end-to-end guarantee of service if you establish a connectivity between a client embedded in the vehicle and a service which is hosted by a centralized server in the cloud. While for this type of connectivity, the guarantee of service which has been negotiated is between these guys, so the V2X apps on the vehicle, on the local gateway here. But since the edge server is co-located or very close to the local gateway, you can make the conclusion that the connectivity between your V2X apps on the vehicle, on the V2X service, or whatever it is in the edge server are guaranteed end-to-end. And this is a major difference. So combining guaranteed bitrate bearer, like plus edge processing guarantee is a means for you to guarantee an end-to-end quality of service between your embedded application on the vehicle and the V2X, the server, which is hosted in the MEC edge cloud. However, there's no you don't win over all the different KPIs. There's a trade-off between reliability, latency, and throughput. So when you negotiate and establish a connectivity which is highly reliable and low latency, usually you have a low throughput. And when this is established, you are negotiating the max throughput. It's clear that if you want to have a low latency and highly reliable connectivity with a high throughput, it's very likely that the network will reject it. And if you try to transmit more than what has been negotiated, there's a rate shaping function inside the network that will discard many of data, and the quality will be worse than if you have established a non-guaranteed bitrate bearer. So keep that in mind. You establish a low connectivity with high reliability level and low latency. You cannot exceed the negotiated bit throughput. If you exceed it, this would be even worse than not using a guaranteed bitrate bearer. So let's now talk about the in advance quality of service prediction. Why is it important? So let's consider that you are on the coverage of a base station AE here, which is collocated with edge server A. And few minutes later, you are moved to a second base station, which is collocated with the second server. During this period of time, you have done a MAC handover, but during this can be more or less long. During this period of time, you may have lose the services, or it may have been degraded, or there are also some cases where your quality of service will be worse than what was you were expecting, because you are driving in a hotspot of very strong fading, or because you are arriving in location where there are many vehicles which all are requesting for high cost demanding connectivity. So it's really key that you are notified in advance about the cost prediction change or even loss for the car to anticipate to take appropriate actions. So that can be, for example, requesting for the driver to take back the control of the vehicle. Or that can be, for example, to upload the HD map of the location where you know you will lose the connectivity. And for edge of the service, it should also allow to take action. So it could be a cost renegotiation, for example. So as you can think about, that is the reason why it has been decided to introduce a quality of service prediction function. This has to provide to the edge service or to the vehicle a predicted achievable quality of service for a given time horizon. As input, it will collect many inputs. So if it will collect, of course, the metric of the radio access network and also some metric of the core network, that's quite obvious. It would ideally get as inputs expected vehicle behavior, but there's also people, so there's no limit to engineering thoughts. So there are people who are thinking, why not also injecting into these prediction functions some third-party data like the road analytics, the weather forecast, the maps or whatever, to anticipate where there will be a very heavy vehicle traffic and so very heavy data traffic. However, there's still today two open options. Where is this quality of service prediction done? Is it done in the 5G core network, or is it done in the MEC framework? From my point of view, there's two types of quality of service prediction algorithms. One which to predict the quality of service change on very short term, and that could be a very highly dynamic and high frequency monitoring, and that will be clearly based on radio access metric on the core network matrix. And there could be, I would say, an algo for long-term quality of service prediction, which can be only detect and anticipate the loss of service when you are driving across the border, for example, or when you are driving to a tunnel, or stuff like that, where you will lose where you can lose the service. So for the first type of option, it's clear to me that it should reside and sit in the 5G core network, because the accuracy of such a quality of service prediction depends strongly on the knowledge of the scheduling algorithm at the radio interface, and also on the policy of the backbone resource allocation. And this can only be done by the telco operator. While the other one algorithm, the long-term prediction of loss of service in case of cross-border driving tunnel, can be done in the MEC, so in the edge framework. So that's it to give you at level overview of the 5G concept on how it will help to do some edge computing. So let's now talk about what ETSI has standardized and what ETSI is being standardizing. So to give you a solid background, solid foundation to develop your edge computing for autonomous driving. So I split this presentation, this part of the presentation into 4 bullets. So the MEC framework as currently specified by ETSI, and then I will focus on the challenge which are still open regarding intra-operator mobility, the scenario when you have multi-operator and then the inter-operator mobility. So as I said, the 5G core network is an open network, and the edge services as a third party can register to the 5G core network. So it can be aware of some event, like when my vehicle moves from cell A to cell B. It can be aware of some network analytic on other course or metrics, which can be used for the quality prediction. But the 5G core network also exposes some API to influence the data routing, as I explained a little bit earlier. It also exposes an API to negotiate the quote, as I said earlier, on to provision the expected vehicle behavior. So especially the vehicle trajectory. This API already exists. So here is what the ETSI MEC framework looks like. So you have the 5G core network here with the main network functions, and you have a MEC platform here, which provides you some services. These services are registered to these different network function and can monitor some events that are useful for the application that you want to develop. In this MEC platform also, you have a service registry mechanism. These registry mechanisms allow you to develop a service that you want to make public. So once you have developed your service and you want to expose it to be part of the MEC platform and the MEC framework and to be visible by other MEC, you can register it. So there, and then there's the visualization infrastructure, which will give where you can negotiate and we can get some computing capability, some network capability, and combining both, you can develop your edge services as a I would say a regular service, which is encapsulated in the virtual machine. So these three services are today standardized. So I put the ETSI reference if you want to cut the detail on the registry mechanism is also specified today in this ETSI standard. So to move a little bit into detail, you develop an apps service for edge computing, and so it can access, as I said, today are three types of services: radio network information services, location services, and bandwidth management services. To access to this is standard HTTP request and subscription. So I put here the type of event you can be notified. So for the radio network interface services, you can be aware or notify about the tail change of my vehicle, for example, so that can allow you to anticipate very short interruption of the service when you move from cell A to cell B. You can be notified and be aware of the receive signal of my vehicle, so that for the current cell and for the neighbor cell, so that allows you to anticipate, for example, loss of coverage and so loss of the service. You can also be aware of some logical information regarding the type of connectivity which are created, modified, released on the associated cost level, so that can be useful to detect some possible quality of service degradation or improvement because of the increase of the congestion or the decrease of the congestion. You can also, so you also have some location services which can tell you where my Renault car are, for example, or when you can also ask, please tell me what are the vehicles on this given location area. And the third service which is today available is the bandwidth management service, which allow you to request for a given bitrate, uplink and downlink. So this is what is standardized today. Let's now talk about what is not being standardized and still open. So again, let's talk about the mobility inside the same network. When you move from the base station A to the base station B, if you are using a 4G network, you will experience some IP discontinuity. So it's I would say, transparent for the vehicle will do what it does to reestablish. So the vehicle will do what it has to do to reestablish the connectivity, the IP connectivity on this new base station, but the service will be possibly interrupted for a few 100 to 1 second. For 5G network, you may keep the IP continuity. So the degradation is much during the transition from CLA to CMB, it's only in the range of a few milliseconds. However, there's still some problem, some application that needs to be solved. Some application on some transport layer are stateful. That means that the execution at time t depends on the execution of the previous time. Or some application depend on the configuration context. So if you move, let's move from the previous, from this coverage to this one, you want to transfer the context of your application from this edge server to this one, ideally. So the question becomes now is how to reliably predict the target MEC where you will arrive, on how to predict reliability the time when the handover will happen. This can be done, I would say, relatively easily using the location services, because with the location services, you know where the position of your vehicle. If you have access to a map, and you have also access to the map of the deploy MEC, you can anticipate what is the target MEC, knowing your expected behavior, and you can roughly assess when it will happen. But there's today no standardized and commonly agreed mechanism to transfer the application state and the application context, and there's no API as well. So let's now consider another use case where on the road, so you have two vehicles and they are covered by two different telcos. So on the blue vehicle has a SIM card with operator A, while the red car has a SIM card with operator B. And let's say that this one wants to make, for example, an overtaking maneuver, and he wants to establish a see-through session with this one. A see-through is a session where the vehicle will request the blue vehicle will request the red vehicle to provide its video. So what's its onboard sensor see? By this means, the blue vehicle can know whether it can safely or not initiate an overtaking maneuver. So for that purpose, it's clear that you need to establish a peer-to-peer communication between the blue and the red, and then you need to establish a tunnel between the MEC of the telecommunication telco A to the MEC of the telco B. Again, today, there is no standardized horizontal mechanism to coordinate and to communicate between two MEC of two different operators. Similarly, there's no standardized API for MEC to cloud and cloud to MEC. On the last So the last concern is, but it's very similar to the previous one indeed, is the cross-border. So if when my vehicle is driving from the French side to the German side and needs to go across the border. So of course it will change from a French operator to a German operator. So at cross-border, what you will do, you will lose the coverage of your French operator, you will do a PLMN scan, discover the telco on which you have a roaming agreement. Then when arriving on the German side, you will reestablish to your services and you have to resubscribe. So if the service was transferred from the MEC, French MEC to the German MEC before or during the cross-border, it will reduce the interruption time. Or alternatively, it will be helpful if the context of your application here is saved before the cross-border into the cloud and downloaded back to the German target MEC just after the cross-border. So if I summarize, so today we have the foundation, which is a 5G core on the ETSI MEC framework, but there are still some mechanism that needs to be defined, especially the MEC to MEC, MEC to cloud, cloud to MEC mechanism to establish fast and efficient tunnel on API are not standardized yet. There are some work in progress about ETSI about that, but this is really important to guarantee interoperability between two different MEC systems, but also to optimize service continuity during mobility at cross-border, between for mobility between inter-operator or even intra-vendor mobility. And again, and also the quality of service prediction and unification is really important to reduce the service interrupt time during mobility. And this is today still work in progress. So let's take about a real example. So I will show you what the use case is. So what is a simple 5G connective configuration? What will be the value of the edge computing for this type of application? And again, what are the environment challenges? So the use case is, I would say, very simple, is the vehicle are receive incentive to share their own road perception. So they upload their perception into a service which is hosted in the edge cloud. So edge perception, road perception, sorry, mean something like very local information of a cone for roadworks. It could be very dynamic, like a bicycle or the vehicle around you. And this edge service will analyze and consolidate all the information received from the different vehicle and download back trustable and real-time contextual information like I don't know, hazardous location, like traffic jam, accident, or whatever you want. This is a use case. So what could be the 5G optimal connectivity and simple configuration connectivity for this use case? So you can negotiate with your telco to have a pre-configuration provisioning of the two types of connectivity, which would be pre-configured when you are attaching to LTE or 5G. And also the routing rule can be pre-configured. So that will avoid that will reduce your software development on the edge services. So when you attach to LTE, you can have an agreement with your telco so that it creates two types of beer, a connectivity which is focusing on infotainment, which will be mapped on EMBB slice with non-guaranteed bitrate beer, so no guarantee of the quality of service. And you may ask also and negotiate with your telco to establish also a second connectivity, which is targeting V2X, but this is, call it as you want, which will be mapped on URLLC, which will offer you which will have a quality of service index of 3. So it means that the latency will be 50 milliseconds on the packet arrays less than 0.1%, and that this connectivity could ideally be mapped on a dedicated APN, so to improve the security, the cyber security. And you can also negotiate with the telco that the routing rule has provision and pre-configured, and the routing rule can be very simple. For the edge, intercept every URLC data for my vehicle, and that's it. So with this type of connectivity and edge computing, your vehicle can be notified by a new road event like an accident or traffic jam. So with a delay of less than 50 milliseconds, with a probability better than 99.9%, if you are arriving in the MEC coverage and the event has already been detected and stored in the edge of this coverage. And if you are on the coverage of edge and suddenly an event occurs like an accident, you will be notified with a delay less than 100 milliseconds with a probability better than 99.8. So it's not 9, it's 99.8, because you will have a packet error rate of 1% in up and 1% down. The second value of this type of edge is that it will do data fusion of the received information. So if 50 milliseconds reports something which looks like an accident, it's a very trustable information for the vehicle receive this information. And it's much more reliable and trustable than the notification of accidents that you will receive for single vehicle. And the second advantage is you can think about each vehicle building in a decentralized and distributed manner their own electronic ERIs on board. But this will be less efficient. This will not as accurate and as safe as when it is done by edge computer. But also it will, we say, not efficient from a collective path separation of view, because here you have a single entity, the edge, which makes the complete computing for all the vehicle under its coverage. While if it was done in a distributed and decentralized manner by every computing, they will all make roughly the same computing, so it's not very efficient. And the third advantage of such service is that it will allow to release the bandwidth for direct communication for B2V. So clearly, this type of use case can take the full advantage of the edge computing. But again, we are still facing some issue about no standardized MEC-to-MEC communication between different MEC systems. We are not still suffering of no standardized efficient tunnel for MEC-to-MEC communication inside the same MEC system, and the in-advance prediction of loss services needs still to be fully specified. So to conclude, I would say that the foundation of the edge computing for autonomous driving are here, thanks to the new feature of 5G CONNECT, thanks to the ETSI MEC framework, but they still work in progress to standardize the MEC-to-MEC communication and to offer some clean and clear API. Again, similarly, there's still some effort to be done to standardize tunnel for MEC to cloud and cloud to MEC communication API. And to also the in-advance prediction needs now to clearly specify where is it done, and how is it notified, and what are the API. And that's it for my side. So thanks for your attention. And if you have any question, I will try to answer.
Thank you, Eric, very much for your presentation. We now have some time for your questions. So again, I would encourage everybody to send in their questions now. The first one we already have, Eric, where will the local edge servers physically be located, and how can one configure them for the application?
Okay, the edge server will be some compute. It will depend on the telecommunication deployment. So now the base station will have very big computing power, and they can split a part of this computing power of this processor. So allocating let's say 30% of this big processor for managing the LTE or the 4G stack, and the remaining 70% for edge computing. And this will be virtualized and offered to everybody who will pay for that. So you can think about edge node, so edge computing, being either collocated with a base station or being an entity decentralized in the core network, and which see a few sets of base stations. Is it clear?
All right, thanks, Eric. I would say that clears up the question. As I see it now, we don't have any additional questions to that one. So I would say for the moment, let's leave it at that. Like every time, if you should have more questions or come up with questions a bit later, don't be shy and send them to us. We're happy to forward those to our speakers. So yeah, thanks again, Eric.
Maybe I have a short comment. So I was always talking about 5G core network functions. Sorry.
Problem.
Indeed, this is a core network function which is completely managed by the core network, and which are based on the provisioning of your SIM, what will be negotiated with your telco, or what is based on the edge service. But so it doesn't depend indeed on the real radio access network. So you can use on the regular 4G chipset today to access to this edge computing, to access to the connectivity with IQOS. You don't need to. We do not need to wait for 5G deployment. We do not at the radio interface. This is what I mean. You can use telematics units with 4G today to get access to this new capability of edge computing.